too many. I think this is just because Marco ran over that we were so late. It's his fault. It's your fault. It's your fault.
Okay, so good afternoon. Welcome back. So let's start the third lecture of Professor Tim Eifler. By the way, just recently, today, or I guess was announced, he got a very prestigious prize of the
Thank you.
Department of Energy. I'm not say how much.
Yeah.
A young investigator.
Yeah. Thanks.
It's an important person.
No.
And actually, Cora just. Who was here last week, was also one of the few recipients of this very prestigious award. So we're lucky to have two awardees as our lecturers. That's amazing. That's not planned.
Thanks. Yeah, the best thing is that it's called early career, so that's confirmation that I'm in my early career. It's really the best aspect of that. Okay, so welcome to the third part of From Models to Data. Just very quickly, so in the first two lectures we had an overview of concepts, we talked about systematics in the last one, and then you might realize that there is again a change where I decided to go a little bit into MCMC and Fisher and actually talk about the desk SRD that you might have downloaded and coded with in the past already, in the past days already. But I think understanding what the Fisher information matrix is, what Monte Carlo Markov chains are, and we'll look at the Metropolis Hastings method a little bit, that could be quite useful. So just a quick recap. This is actually our problem, model space, data space. We seek this kind of a connection. And we've discussed this equation and this slide at length. And that's actually one of the most important slides that I would hope you guys can take away from this lecture, because it describes all the different ingredients, starting from an actual equation. What do you have to do if you want to do a cosmological likelihood analysis? And in the last lecture, we went a little bit deeper into what actually goes into the model vector. We had the example of weak lensing, and in particular, we discussed the trouble with systematics. So basically, what happens if you have a systematic in your data vector and you see that your contours will be off from the actual input value, and in order to bring them back, you have to remove the systematic. But not only do you have to remove it, you also have to account for the uncertainty in knowing that removal process. The removal process has an uncertainty that is built in, and that needs to be parameterized in the likelihood. And then, even though you are back-centered on the true value, you actually get an increase in your contours. And because the removal process is not perfect, you will most likely have a residual offset, and you have to make sure that your parameterized uncertainty is still large enough such that you are centered on the true cosmology. So don't be too speculative. Small error bars are not the only thing in life. It's really not. And we discussed this at length, which is the main question that is being posed to the community today as well. Namely, if you find discrepancies amongst different probes, what is the underlying problem? Is it, or what is the underlying mechanism? Is it new physics? Have you actually discovered new physics? Or are you just not able to model the systematics precisely? And claiming new physics is controversial, so you should first check on the systematics. And yeah, I think it is important for junior people to actually think about how can you, what would be the strategy that you would develop in order to deal with such a scenario or to avoid such a scenario in the first place. And the main ingredient in order to avoid this is to have a very, very long suite of tests, of null tests that you do on your data. You define it before the experiment, and you have to think very hard what can possibly go wrong in my data beforehand, not after you've gotten this disaster. Beforehand, you have to think about it very hard. You have to design the tests, and you only move forward once these tests pass. So it's usually a staged process. Some tests happen very early in the data, some happen later. Some happen only on the theory side, some involve simulations, other involve external observations, but designing this suite of tests is one of the most complicated aspects of cosmological analyses, and doing that requires training, requires discussion. That's what we do in these largish collaborations. And sometimes we also fail in designing all the null tests. And then it is important that we discuss afterwards what we do very clearly in the paper. So don't try to hide stuff that you've been doing after you've seen this kind of a result. I think there's great value in explaining to the community what you've done at the beginning of this process and what you're doing once you get this result, because it's a different mindset in which you operate. Okay, so today we'll talk about MCMC, Fisher, and then for the second half we'll move to the desk SRD. Maybe quick question, who here has downloaded this zip package of 300 megabyte? Has everybody downloaded it? Perfect, almost. Great, and who is able to run it? Okay, so running all the way to run Fisher and it worked? Okay, and who has tried to install it and it has completely failed because of some dependency? Okay, can you quickly say what? Sorry, I'm curious.
Every step required installing something extra, and I kept installing them until I reached the point where I couldn't anymore.
Okay. All right. We'll have a look. Later on, I'll just, this is going to be an unusual lecture. I'm going to go around and try and help individuals who might be stuck. But that's only the second half. So I hope everybody brought their laptop. Okay. What connects model and data? We've discussed this. This is Bayes' theorem. This is the posterior of model given data. This is the likelihood function, data given model. This is the prior information, and this is the probability of the data. That's usually a constant. The evidence, it's important when you do a model comparison. For our MCMC, we will later realize that it is not very important. I want to introduce one important thing, which is called the conjugate prior. So a prior is called a conjugate prior to the likelihood if the resulting posterior that you get has the same, or is taken from the same distribution family as the prior itself. And there's already examples there. So for example, if your likelihood is a multivariate normal or just a univariate normal, actually works with both, with a known variance and only the mean is the parameter in question, then the prior, the conjugate prior to that would also be a normal distribution. And what we are going to look at now is where the likelihood is a binomial distribution and the prior in this case is a beta distribution. But this expression will come up a lot when you take some stats class, so it's just useful to know what does it actually mean. People are always talking about conjugate priors. They're useful to build. It's great if you have a conjugate prior to your likelihood. So what does that mean? It just means that the functional form, or that the family of distributions that the prior is taken from is the same as the posterior. So prior information, you do something to it, get the posterior, same distribution form, then it's a conjugate prior. Okay. Is that mostly clear? Is that new, conjugate prior, or who has heard conjugate prior already before and knew what it was? Okay, one person. Good. Then that's new. We'll get to that. This next slide. If you go to probability distributions on Wikipedia, you will see a very long list of functional forms that all have cryptic names, and that's one of them. But it's exactly this. Sorry? Why is it important? No, it is. So in this case, as we will see, it allows you to actually calculate the posterior distribution analytically. So you don't have to map it. You can actually do the analytic calculation directly. And let's quickly go through this example. I think then it'll become obvious. So this is a coin toss example. have a coin, you toss it 100 times, 61 successes. That is the outcome of this. We know that the posterior is proportional to the likelihood times the prior, and the likelihood of this is parameterized through this. Let me see. So this is the number of tosses. That's n, and that is actually h. Sorry, I should have written that this is h. The prior in this case looks very, very similar. This is a beta function. It's parameterized through two different parameters, alpha and beta. And you can give them different values from 1 to 100. And I've actually, on the next slide, we will go to an IPython notebook, and there you can see how this looks like as a functional form, and you can play around with it. But if you calculate the posterior like this, you will get, again, a beta function. So this is a conjugate prior to this likelihood, because the posterior, again, has the same functional form as the beta function. And you can do this analytically. There's no need for you to run an MCMC, actually. You can do this analytically, and then you can insert the corresponding values, and you can plot the posterior directly. So this is a case where you have the ability to analytically go from your data space to the posterior space. From coin tosses to the posterior. But usually that's not the case. Usually this is a much harder problem, and that's why we have MCMC sampling. Okay, so IPython Notebook 1, if you can go to this link, it's a Dropbox link for me. I didn't know how to share links here, so you'll have to read it off and type it. How would I share links with them? There's no...
I cannot think of a...
Okay. So this is already an exercise. You should start up your IPython notebook, and you can go there to download the MCMC tutorial IPython notebook. And I'm going to leave this link here, but then very, very shortly I'm going to switch to the other screen, and we'll have a look at that notebook. If you don't have a laptop, I do encourage you to work in pairs. I generally encourage you to work in pairs. That is always helpful. But this is a class where it is going to be, well, essential to have a laptop of some sort. The first person who successfully downloaded this, please let me know, because then I know that I've set the right... Yes? Okay. Great. Okay, I'm going to exit here. I'll leave the link there. This is tricky now. No. This one goes away. Okay. Right, I'll have to rearrange this a little bit. All right, I hope everybody's got it? Not yet? Okay. Okay. Sorry, you didn't get it? Who's not gotten the link? Okay, I'll wait 2 more minutes. Freeze the phone.
Yes? Oh, thank you. Okay, you can.
Yeah, if there was an email list, I would have sent it to all of you, but I didn't have that, unfortunately.
Thank you. So you can.
Yeah? Okay. Everybody got it? Fine. I now realize that, okay, oh, it's going to be a tough day for my neck. All right. Okay, so here you can actually see, sorry, almost, see. First, come here. Okay, number of coin tosses is 100. H, number of successes, is 61. P, probability, H over N. This is the binomial distribution as a function of number of coin tosses and probability. These are the two parameters of the beta function. That is our prior. And here is the analytical calculation of the posterior function. So that's actually everything you need for the first plot. And so if you run this, you should get this nice figure over here. So just very quickly, what do we see? In blue, we actually see the prior. And the prior is, given that it is a coin, we would think, 50-50. That's the prior. That's why this peaks here. Now, this prior has a certain width, right? And the width of this prior determines how informative is this prior actually. And I think there was a question at some point, what happens if the prior and the likelihood are competing? Why can't I run the longer chain and then I should get the true result? And we can see what happens here later if we make this prior more powerful. What does it mean to make the prior more powerful, just visually? Yeah, you make it more narrow, exactly. So then let's have a look at the other ingredients. So here in green, we have the likelihood. And in red, we have the posterior. And all of these are calculated analytically, right? I didn't run any chain or anything here. This is just analytic calculation. You can do the mapping directly prior to posterior. Yeah, and then there is a maximum likelihood estimate here, which is the peak of the likelihood, and the map estimator, which is of the posterior, and they agree if the prior and the likelihood agree. But let's not care too much about red and green here. Let's have a look at what happens if we change some of these values. Okay, and that's exactly what I would like you to do. These are the parameters that tell the prior what the width is supposed to be. And you can now set them to 5, and you can set them to 100, and just redo the plot and see what happens. And I would like you to do that now, and then work as a group to come up with an explanation of what you really see. And one of you in that group is then going to present that, or explain that quickly. And I'm going to be very invasive and just walk around and check what you're doing on screens. Wait, you don't have a laptop? You don't?
Can I do it?
Yeah, you could probably do it analytically and just draw it. That's what? Oh. Yeah. I see. Oh, you're checking on. No, very good. Yeah, yeah. Yeah, and here I can actually escape from the camera. Look how confused it is. Looking for me. So if anybody has a question, right, definitely do ask me. That's now why I'm here. You asked the question about the prior and likelihood competing, right? Mm-hmm. Like, okay, does this help if you see what happens?
No, I just
okay.
brought my note.
Okay, sounds good. Yeah. Yes?
I just got
got here and I'm confused. Where is that file or the notebook?
Oh, that is on Dropbox. And did you see the link?
Oh, no.
Okay, well, let me bring back the link. Oh, yeah. So it's here.
This one.
How do I get rid of this? Great. Okay, some people are much faster in having their IPython notebooks up, etc. So I'm going to give this 5 minutes for everybody to bring their IPython notebook up to speed, download this, play around with it. Yes?
Maybe this is the version of Panda that because I tried to install it and I should have it now. Maybe I have to run again the.
What is the exact?
Stop and restart the kernel.
Okay.
Yeah, I think you actually have to do pip install pandas or something like that. I don't think.
Yeah, I did.
Okay.
I did.
Yeah. Oh, then you have to restart. Yes, that's right. Yeah. Yeah. Is this working for you? Okay. Just okay. See, you're way better than everybody here. Okay, it's very nice.
I'm not sure exactly what is being done.
Well, I mean, you see what happens to the prior, right?
Yes, I just plotted prior.
You're right. Well, but I mean, no, there stuff happens to the posterior.
So you're plotting those functions that you show, age and
Yeah. Yeah, that's right. Yeah.
there's no operation, no integrals.
Sorry. No, you can just call me. I come to you. You don't have to. Okay.
I just want, because I was bringing my notebook, so what do you propose us to do?
Right. Okay. So just a quick recap. Now the idea is to change these values over here, A and B, because they enter the prior calculation here. And I've defaulted them to 10 originally. And so in that case, the prior is extremely weak.
I think it would be useful to show again the formulae for the
Okay.
likelihood prior to what we're plotting.
Okay, we can do that.
For me, it would be useful. Usually it's lowest ones. So that's what we're plotting.
Yes,
So A and B is what? Alpha, B?
alpha, beta. Yeah, sorry. Yeah. I'm Greek. I'm a Greek person. No.
So that's how I'm supposed to see the competition between the
Yes,
prior
exactly.
and
Yeah,
okay.
yeah. And this is a simplified example because you can calculate the posterior analytically directly, right? You don't have to do MCMC. And it's a rare case. Usually MCMC is necessary. Yes?
Because I'm trying to put different values, really different, like
Okay.
values alpha and beta.
Yeah?
You get this, no? So this doesn't make a lot of sense. So
Why not?
why not?
Yeah.
I don't know.
Why does it not make sense? It makes sense. It's a specific case.
Okay.
So this is exactly what I would like you to see in principle, how these different curves change if the prior becomes stronger or weaker.
See.
So
Okay.
And then you have to make the connection, what does this correspond to, right? I mean, we have a coin toss example, and our prior is assumed to be 50-50. But what you gave it here, right now, the prior is no longer centered on 0.5, it is somewhere centered here. So at that point,
This is the prior, but then what I get from the data is something totally
that does not change. That's actually just moving up and down.
same.
Yeah, that's the data. Just give it some more values and see what actually shifts and what doesn't shift. So I want to give a couple of hints. So our experiment really is 100 trials and 61 successes, right? That's our data. It's not changing in this IPython notebook unless, unless of course you change these values over here, 100 and 61. And you can. But for now, we only wanted to change values that affect the prior itself. So only A and B. And if you only change A and B, then what is supposed to shift is blue and red. And green, because our data does not change, is going to be pretty much the same. If you want to change the data stuff, the information that comes from the data, you change N and H. But let's first do the prior thing. Okay, so which group has a result? Is there someone who has tried out a couple of A and Bs and can give some interpretation of what they see? And I will actually copy that here. Yes, okay, thank you. Wait, 1 second, 1 second. There we go. So what did you do? This is what we start out with. Oh, wait, I need to give you a mic. I think that's necessary. Sorry. There you go.
Yeah, if we change the prior to be narrower and more informative, then the posterior tends to go towards the prior.
Okay, what do you want me to set it like?
What?
Which numbers should I set it to?
Yeah, first we try to use less informative priors. We set it to 5.
Sorry. Different screen.
5, 2. We test a lot of numbers.
Right, okay, so what happens here?
Yeah, then your posterior agrees more with your likelihood because your prior is less informative.
Yeah.
But if you put A and B to be 1,000, for instance.
1,000? That didn't work for me. That worked for you?
Yes.
Wow. Okay. Your laptop is more powerful. Wait, let me see. I want to know that now.
Okay.
Okay. That's very weird. Okay, but sometimes that happens. Yes. Please go on. What do you see?
So your prior is much more informative now, and your posterior tends to agree with it. And your likelihood is not much information to compete with the prior.
Yeah. So the likelihood does not have enough information, even though this looks smaller compared to the previous plot, right? That's the same curve. That has not changed. The only thing that has changed and has changed drastically is actually the prior here. And then consequently, because this is now so informative, it's pulling the posterior towards it. And what does that mean in terms of the coin toss thing? It means that in this experiment, the person much, much more strongly believes or has reason to believe that this is a 50-50 experiment, right? The person before was not that certain. So if you set this to 10-10, that corresponds to a person who looks at the coin and says, this doesn't look like a 50-50 coin. I'm not so sure what it is. I'm going to give it 50-50, and it's going to be broad. But this person here is like, my coin is perfect. I know it's 50-50. I'm going to put a super strong prior here, and that drives the posterior. And the data itself, that just stays the same here. Okay, cool. Let's see. Do we want to? Yeah. If you increase n here, well, let's do that. Okay. Let's play around with n, not necessarily with h. Let's leave h as is, and let's put this one back to 10. And just quickly see what happens here. If you give this 1,000. Oops. Wait, there's a mistake. Oh, okay. That's better. Okay, yeah, so if you add a 0 here, you should better add a 0 there. Otherwise, it's otherwise it's just a different experiment. But yeah, play around with those a little bit and see how the data is actually driving the posterior. And then we're going to move on because this is already taking a bit. Get my microphone back. Thank you. Yes?
So if the person believes a very strong prior,
yeah,
then posterior becomes that. But I changed this to 91.
Okay.
But the person believes it's a very strong 50-50.
Yeah.
But actually what the person believes can be wrong. But then posterior is still very close to...
Yeah. The person really strongly believes it's 50-50.
But 91 is a success.
I know. No. But I mean, you can see the data has moved here.
Yeah.
This is 100, so the data has moved to 91 more or less. 90, yeah, this is 91. But the information that you get from the data is still not powerful enough to compete with the prior. Look how much uncertainty you allow for the prior belief. If you had to quantify how much uncertainty does this person
you combine
give?
These two, so you multiply these
yes.
two, prior with
exactly. Yeah.
But then this means that our belief, how much uncertainty we allow for prior, is really, really important.
Yes. Yes. You have to be aware of that. Yeah.
So we shouldn't use strong priors then.
Unless you have a good reason to. I mean, sometimes you have a very good reason to use a strong prior because you might.
Actually, here also we have, because we know the coins are.
You don't know that. I could tweak the coin somehow.
Yeah.
Yeah.
What about if you decide to use the flat prior?
The flat prior here. Yeah. Well, the flat prior is so that would be
0, 0.
Yeah, I'm not sure if the beta function takes 0, but you can try.
Yeah, it takes 0.
It takes 0. Okay.
Oh, then.
Yeah. Is 1 and 1 for beta? Okay. Yeah.
1 and 1, not 0, 0.
1 and 1. Yeah.
A and B 0 goes 1 over x.
Yeah,
Yeah.
so it's flat prior.
Yeah.
And
So, I mean, if you're a person who wants to be driven by the data only, right, you pick a flat prior. That's right. In this case, that is a non-informative prior. That's correct. And then you can and then your experiment gives you all the information. Then it's only the experiment that gives you information.
yeah, I think I would be choosing flat priors, like in my opinion.
Yeah, okay. You might.
Because actually, I
But then what's your conclusion here?
my conclusion.
Yeah. What is the coin?
61.
Yeah.
Yeah.
You happy with that?
No, so it's not a very good informative posterior.
Well, I don't know. Maybe the coin is a little bit tweaked. I mean, in this case, you know what the truth is, right? Because you put the H there,
Yeah.
right? The H is the truth in this case.
Normally, but you're observing the H. You know the H.
Yeah, you know the H. Well, I mean, there's a difference between. No, sorry. So you only know. We don't know what the truth is here. We just see the experiment. Right. And if we let the data drive the experiment entirely, then our conclusion is that this is a slightly biased coin. Right.
Yeah. Although 61 is a rather high chance if it is a 50-50 coin.
Right.
So that's why.
Yeah, but we yeah. So we're not going into hypothesis testing of like what is the probability given that the coin is real. We're not going to do that. I just wanted to show the interplay of prior and posterior and likelihood, and especially make exactly that case that priors can be extremely powerful, right? And if your experiment is more complicated than this, and the data drives it very, very far out, right? Like you put this to 91. The data is going to drive it all the way to the right. And that could be an interesting result scientifically if it was very complex. But you have such strong belief coming from a different experiment that that it brings it back, and then you don't see the interesting result of your data because you have such a strong prior belief. So I want to make people sensitive to the fact that the prior is super important. Yeah. Okay. Does anybody want to quickly comment on what happens if you increase n and if you increase h, or if you change these values? Right, do you perhaps want to quickly recap our conversation that we just had? I thought that was actually useful. Okay.
Recap. So
Yeah,
if you don't use a strong prior, then our posterior is completely driven by the likelihood function, so data itself. But as we increase the A and B numbers there, our prior becomes really, really strong. So we have strong belief that our coin is 50-50, let's say. Then our posterior becomes really close to prior. So although the data is different, since we have very strong belief in the prior, so we don't allow any uncertainty in the prior, the posterior distribution follows the prior. So our belief in prior, or how we choose prior, is extremely important in the main result.
Yeah, and there's a bigger picture, and I wanted to come back to a slide that I showed at the very beginning, which is this. So here we actually have two different experiments, Planck and DES. DES year 1, recently published. This is the Planck experiment, the famous satellite. And this is the combined contour. And conceptually, and you can see that over here, there is no difference to the experiment that you've just seen, right? You can define Planck because it was because Planck happened first. You can define Planck as the prior information, and you can define DES as your data, the data that you've gotten new. And then the question is actually, and that question was posed in our collaboration, can we combine these two? Right? Or are they so far apart that it is not allowed to actually combine them? And that is a very, very similar question as the one that you've seen here. So if we now move the likelihood to something crazy, not crazy, but it's just the data tells you whatever it is, right? You have a very biased coin. So you take this one. Now our data tells us this is the outcome of the experiment. Our prior, which is pretty strong, tells us it's 50-50. And what have we done here? We've actually combined the two. But the question really is, should we have combined these two? If you look at them individually, it's pretty clear they're so discrepant. We have to resolve this discrepancy first. We shouldn't combine them. Right? They are inconsistent. They're clearly inconsistent with one another. So those are thoughts that you have to have when looking at priors and when looking at data. And the idea was brought up here that if we want to look at what our data is telling us just in and itself, we should set this to a flat prior, which is 1. And now the blue thing is uninformative. It's a non-informative prior. And what we get is what our data tells us, which is 910 heads out of 1,000 tosses. Okay? All right. That was actually longer than I thought, but I still think this was very useful. Very happy with the discussion. Well, thank you all. Let me quickly see. Right. And now we're moving on. Yes? Yes, please. Wait, microphone. Microphone is coming from the back.
So if we use Planck as a prior and DES data as the likelihood, we get that the other contours. But if we do the opposite, are we going to get the same contours?
Yeah.
Yeah, right. Okay.
It is commutative.
Just okay.
Yes. But I mean, in both cases, you have to go through. I mean, usually the ordering in time is given by which experiment happens first, right? That tells you what's prior belief and what's likelihood.
Yeah.
That's usually how it happens. But the thinking process, the thought process is exactly the same. Namely that you have to see, are they consistent? Then you combine. Are they discrepant? Then you have to think, well, why are they discrepant? It could be physics. It could be systematics. Okay. All right. Moving on to so this is beautiful because we can do all the calculations analytically, right? And I want to stress that that is not true in general. That the posterior can be calculated so easily. I mean, that doesn't take a lot of time to actually calculate this. Usually this is a more complex problem, and we need something like MCMC sampling. So we sample from a distribution that we hope is very, very similar to the posterior itself. And that we do that a couple of times, and then we get some kind of chain that is becoming stationary, and then it is, and then that is our best guess for the posterior. Okay, I think I've said, so computing the posterior on a grid, which allows you to compute the evidence, to compute the denominator through some marginalized likelihood, that's usually not really possible in a high-dimensional parameter space. So here in this one-dimensional case, that would have been easy, right? You just take the parameters, you give it 200 different points, and you can actually calculate the evidence just as a Riemann sum. That's not too hard. But the computation scales as the number of grid points, or number of steps, as I have called it here in my rush, to the power of n. And n is the dimensionality of the parameter space. So for DES, where we had 26 dimensions, 26 different parameters, even if you were to just go 20 steps in each and every one direction, and you would compute the likelihood at each and every one point, and then you would sum over this multidimensional grid to get the evidence, and then you can calculate the posterior properly, that would take of order 10 to the 20 years. And that's true for likelihood codes that only take 2 seconds to compute the likelihood, and not every code does that. So that's too long. And what people came up with, and I was over lunch told that that was Fermi. I read that it was a development at Los Alamos, actually. But
Fermi was at Los Alamos.
At that point in time. Okay, it was Fermi at Los Alamos. Perfect.
Fermi, Metropolis, all this.
Okay. Yeah, I really have to buy a history book. I agree. Oh, that's good. So we don't map the posterior, but we sample from a simple proposal distribution. where the next step in the chain is only informed by the previous step, not by those that actually happened before. And then the hope is that this MCMC chain, or that this chain, this array of steps, that it will become stationary, which means if you add additional steps, it does not change the posterior anymore. It kind of wobbles around a little bit, but doesn't really change it. And once you've done that, then you've gotten a map of the posterior. So this is also what happened here in these contours. This is only 2 dimensions, but overall it was 26. The MCMC walks around. The next step is only informed by the previous step, and then you have an acceptance or rejection criteria. And then once these contours do not change anymore, they're called stationary, and then you hope that what you've sampled corresponds to the posterior. And that's it. And that is MCMC and Metropolis Hastings. And the easiest implementation of this is actually the Metropolis Hastings walk. So what do you need for this? You need a target distribution. And the requirement for this target distribution is it should be proportional to the posterior. And we'll get to that. That's an easy one. You need a proposal distribution. There, people just take a Gaussian. Okay? I'm just mentioning the ingredients. That's all you need. And then you need a uniform distribution to do the rejection criteria. Okay, so here we already know that's a Gaussian. That's easy. Here we know it's a uniform distribution. That's easy as well. So let's have a look at the one ingredient that we need, which is something that is proportional to the posterior. What is that? Well, we've seen that a couple of times, and we know that here, the likelihood times the prior, that is actually proportional to the posterior. It is equal if you also know the evidence, but we don't need equality. We just need proportionality. So these two, that is our target distribution. And usually you can write these down. This is hard to compute. We've mentioned that a couple of times, and we've mentioned that for MCMC that's just a constant. This is actually something that we can usually write down. And so then let's have a quick look. Conceptually, what does Metropolis Hastings do? So you pick a starting value in parameter space. You call it P. You compute the target distribution for P. So what does that mean? You feed P into this equation. So you can write down the likelihood as a function of parameters. I've shown a couple of slides. For cosmological surveys, this can be quite hard, right? You need to be able to predict the data. You need to be able to predict the model. You need to get a covariance matrix. This here, the likelihood, is usually a multivariate Gaussian with all the ingredients. So this can be complex, but this is exactly what people in collaborations work on, to build code that predicts the likelihood. And the prior, we've discussed it at length. That is your prior belief for a given parameter, right? That's what goes into this. Okay. So for a given value, P, you can compute the target distribution, just multiplying likelihood and prior. You draw a new value, P prime, and that is obtained by taking P, and then you add some delta P, and delta P is drawn from this other ingredient that we need for Metropolis Hastings, which is the normal distribution. So you just have a normal distribution. This is 0, but this normal distribution has a width, right? And that is actually one of the parameters in the MCMC that you can fine-tune. The width of this distribution that determines how far of a step do you make in parameter space. So if this is your data vector and you want to go to P prime, then you draw this delta, plus delta. You draw this delta out of a normal distribution, multivariate normal distribution usually. And the width of this distribution that you assume will determine how big a jump you make. And that is an important ingredient to fine-tune, right? Because you don't want your MCMC, if you want to sample a very broad, large distribution, to only make teeny tiny steps, right? So if your posterior here, sorry, coming back to this one once again. If your posterior over here is spanning this range, as indicated by these contours, but you only allow teeny tiny steps that only vary here, then it will take the MCMC forever to converge. So this parameter, this sigma, is important for you not to sit in front of your computer forever. One of the fine-tuning parameters. Okay, you compute the target distribution value for this. So now you feed this new data vector, a new parameter vector into your machinery. You compute the target distribution for that, and then you calculate the ratio of these two probabilities. Right? You get two values. You just calculate the ratio of that. And then if that ratio is larger than 1, you accept the new point, you jump. And if it's smaller than 1, you accept the new point with a probability rho. And how do you get that with a probability rho? Well, you draw from the univariate distribution between 0 and 1. You just randomly draw a number and you compare it to rho. Right? So that's the third ingredient. Univariate distribution, 1, 0. You draw one number, and whatever that number is, let's call that number not p. Wow, let's call that number x. You just compare that with rho, and whichever one is larger decides whether you accept p prime or whether you throw it back, and you draw again from this Gaussian. Okay? It's a very simple process that happens, and it's actually very easy to code up. And that should happen if you just scroll further down in your notebook. That should be there already. Dum-da-dum. Okay, because it's already late. So it's the same example. We have our target distribution. We again have coin tosses. We again have the outcome of our experiment. So this is 100 tosses. We have our prior. But in this case, we're actually not computing the posterior analytically, which we can in this very simple case. In this case, we're running an MCMC, as I've just described on the past slides. And there is one important or one interesting parameter here, which is the efficiency of the MCMC, and that is the number of points that you actually accept. Right? So here, you're running something that's rather inefficient. Okay, so now let's have a look at this. Oh, no, scrolled wrong. Wait, was that the outcome? Actually, let me just run this again. I think I played around with this a little bit. Yeah, why don't you also run this in parallel? And this is going to take a little bit longer, shouldn't be too long. And then there should be a number that tells you the efficiency of this MCMC. Okay, that looks much better. So those were some old values that I ran. And then if you want to plot it, you can do that here. And here again, you can see this is your prior. This is your posterior. And this is the true posterior in dashed. Okay. So have a look at this, play a little bit around with these values, and try to understand what this code means compared to the outline that I've just explained here. Right? That was rather simple what's happening here. Try to map the code on this concept, and try to play around with it a little bit and understand it. And then in principle, you have a Metropolis-Hastings algorithm coded up here for a one-dimensional case. So it's the same things to change. Change the prior around, change the posterior around, change the likelihood around, and see what it does to the posterior. in particular, do play around with this sigma value as well and see how it changes the efficiency and try to explain why. Yes, great question.
I don't know, but this is too clear for me. I changed the sigma value to a very thin, right? So the efficiency increased a lot. It's almost 100%. But the posterior, the sample posterior is very different to the true posterior.
Well, it's not very different, right? You're referring just to the height.
For example, in the you're looking for the sigma level, here is going to be different because here you have the tail. And this means that the efficiency is not a good parameter to trust.
No, the efficiency is not the only parameter to trust at all. Yeah, that's right. Because in this case, and that's a very good point. Sorry, other way around. You don't perfectly sample the outer regions of the distribution, right? And that's because you've given it so little freedom that it doesn't want to go there.
So the efficiency only provides a general vision, a general understanding of the. But it's not a parameter to know if the chains converge.
Yeah, it's not a sufficient criterion for this being great, right? You know it's very efficient, but as you see, that doesn't mean that you're doing a great job. It just means it's accepting a lot of points.
Yeah, it's also efficient because you are inside of the.
Exactly. That's why so you can see the connection. If the efficiency is high, you're accepting a lot of points, so you're very close to the maximum likelihood, but you're very likely not sampling the outer regions good. So an efficiency that's close to 1 is actually not great.
There is a particular value that you can trust.
I actually don't know. I don't know. Yeah, that's a good point. That's interesting. I don't know if there's something from first principle theory that is a good value. I don't know that. But I don't know that much about statistics, I have to say. Like, underlying theory is like, I use stuff and I roughly know what the knobs are, but yeah. And you can see if you do the sigma in the other direction, right? You can see what happens then as well. Yeah. I'll be there shortly, yeah. Yeah, I'll be there now. Yes.
Something interesting is happening.
Yes.
So if I increase the number of samples.
Yeah. No, I have actually not done that. Okay.
And wait, what? It was dying before. I was getting a division by 0.
Okay.
Now it's accepting it. But before it was crashing. Before
I had the same crash. That was when
happened?
I don't know.
Okay.
That was when I was preparing it before the lecture, and I didn't quite understand why.
I tried. It's not in here. It never goes to this if. It's from this guy is returning 0.
Yeah.
So okay, it's just a weird stuff. Okay.
If theta is small. Yeah. Okay. Okay. You're saying it's not this error. Yeah. Well,
yeah, I place a print, but it never triggers, so I know it's from here, but I'm not sure why.
Okay. Yes. Yeah, you can call me Tim. Please call me Tim. It's so weird.
I didn't properly understand the last part. Where you say you define the rule and then you take random value from 0 to 1.
So rho So you have two probabilities that you calculate. One from the first step, from the previous step, and then you calculate a new probability from the next step. And you compare the two, right? And if the new probability is larger than the old one, then rho is larger than 1, and you will take the new one. That's, you're moving towards the likelihood. And if it is smaller, then you don't immediately want to reject it, because you don't want to be, you still want the MCMC to probe another region. So there is a probability with which you will accept this new point, even though the likelihood is smaller. And that probability is the ratio between these two. So you have, ratio of old probability, ratio of new probability.
Okay.
90%, whatever, 30%. You take the ratio of those. That gives you a number. And then you now want to have a random process that decides whether to accept it or not. And so you draw, no, sorry, that's not right. That ratio is determining the probability with which you accept it, right? So if the old probability was much, much, much better than the new one, right? Then you get a very, very small number. The ratio is going to be very small. It's going to be like 0.01. And then you draw a random number between 0 and 1, and only if that random number that you've drawn is smaller than the probability, then you accept it. So for 0.001, that's almost never going to happen.
You eventually want to accept things to become efficient, yeah? Because
Yeah.
that's like total number of trials versus acceptance is the efficiency.
Yes. Well, so here's the thing. If something is extremely efficient, then that means that you are always in a very high probability parameter space. You're always very, very close to the maximum likelihood point. Right? If the chain is always accepting stuff, then you're never moving to the outer regions.
And that's bad.
Yeah, because you want to sample the wings of the distribution as well.
Sigma there, this is what? Sigma of what?
That is the sigma, that is basically you can say the step width for the next step. How far away are you going to go?
Okay, so when I increase it, the efficiency decreases.
That's right. But you will go into the outer regions. And the outer regions are good to know too, because you want to map the whole probability distribution. You don't just want to map the very super inner part. You want to see the wings. Yeah.
So the efficiency is just not the number I want to maximize. I just
No, you
care.
don't know. Well, you care a little. You care a little. If it gets super low, then it's bad. But you don't care. You don't want to maximize. That's right. Yeah.
So the sigma, does it have something to do with the time of the computation? Because
Yes.
maybe
Yeah.
when you change the step, you have to take
because of efficiency.
Yes, because of efficiency. That's right.
So if you don't have much computation power,
Yeah, I think. I mean, these are more like factors of 1.5. You're not going to gain factors of 10. And the problem is if your efficiency is very high, and you still want to map the whole distribution, you have to wait extremely long until the chain goes there, because there's so low probability for it to go there. So it's a balance.
I intentionally added 0 to the meters, and it took a very long time for it to compute.
Yeah. That's right. But that's not. But in this, so if you choose a narrow sigma, a small sigma, right? So you allow only few steps. You allow only small jumps. But if you give it very many iterations, it will eventually go into the tails of the distribution at some point, right? So that is the trade space, and you want to find a balance where the step width is such that with few iterations, it maps the whole thing nicely. That's the goal of the whole game. Yeah. Yes?
Here we have defined the sigma like 0.
0?
Yeah.
No, that doesn't work.
Yeah, but it works because...
No. Sorry, can you make it? I can't see that. Can you turn it a little?
All right, you're right.
So you get an efficiency of 1. Yeah, but I mean, you can't give this 0. It should break. It's
It's just
Yeah.
breaking the program,
Yeah.
right? Because
yeah. There should be a minimum width of this. Okay. Thank you.
Eu te dou o meu, você quer?
Jesus Christ. Okay. So there's been very good discussion already that I had with individual groups. Who would like to quickly summarize what they've done, what they've seen, what their conclusion is for this? Don't be shy. I know that you guys have done very interesting things. Yeah? Okay. Excellent. I think I lost a microphone somewhere. I'll take this one now. Oh, that's great. You raise your arm and then give it to me.
Yeah. So actually, we decide to broke your code.
Oh, to break? Okay. It's not my code. There's actually the link where this is taken from is at the top box of this. So yeah.
Yes, but actually we played with Sigma in order to make a kind of burning, and we plot the chains.
Okay.
So the life is beautiful when you work with a single parameter, because we put a very, very tiny sigma, like 0.01, and everything converged very quickly. So it didn't affect our results. So in order to break your MCMC or this MCMC, we decided to put sigma like 1/10,000. But even like this, our chains were converging to the right posterior.
Really?
But actually, in the end. So I know that if I run for more 10,000 points, it would be some sample that would be similar to what we expect.
Okay, well, let's have a quick look at this. So you said sigma being very, very small. You get a very high efficiency. And then you plot this, right?
Yes.
Okay. So what do you see? Are people happy with this result? Are you happy with it?
Okay, it seems okay.
Yeah, I mean, you're comparing the red histogram and the red dashed line, right?
Yes.
Okay, so what are people's opinions? Is this good? Are they worried about small sigma? Depends somewhat on the prior, yes, for sure. But what happens if sigma becomes very small here? What did you do otherwise? This one?
Yes.
Okay. Oops.
Oh, sorry.
Sorry. Typo. Okay, that's gonna.
So we also changed the initial condition in order to make our chain fair. We are trying to play with the code. So.
Okay, no, that's very good. But so did you see a trend?
Yes, for the small sigma, the chains were walking to the right place, to the maximum likelihood.
Yeah, so so now, okay, with 1/10,000, you actually get an efficiency of 0.97. Now, if you plot that, okay, the effect that I wanted to carve out, oops.
Yeah.
What have I done? No, there's something that is wrong. Sorry?
If you look the chain, even for this terrible case, we can see that if we run for longer, we put more points in our chain, sometimes it would converge for the best likelihood.
Yeah, but in this case it does not.
No.
Okay.
But I mean, when you look at the chain, you're looking that we are basically plotting the burning here.
Yes, that's right. You're still plotting the burn-in. So, I mean, one of the problems is if you make sigma too small and if you make the efficiency high, right? Efficiency sounds good, right? Closer to 1 sounds great. But there's problems with that. You mentioned that, right? Would you quickly say why? Sorry.
Yeah, basically, when the efficiency is so high, it means that you are inside of the true posterior. So you are accepting all the points, but you are not able to sample the full shape of the posterior. So you can lose information like, I don't know, sigma levels. Of course, you have the best fit, but you don't get the sigma levels. That is something very important.
Right. So the problem is if you have a starting value that's very, very far away, and then you have a sigma that is very, very small, right? You're not moving towards the maximum likelihood. So this is what's still called the burn-in phase, which should be removed later on from an MCMC. And if you have a very small sigma, you run the risk of having an insanely long burn-in phase. That's one of the risks. But then exactly, it's also right what you said, that if the sigma is too small and you are already inside the actual, and if you're already close to the maximum likelihood point, then you're still not moving away a lot. You're not moving around. So you will never really probe the 2 sigma region, the 3 sigma region, etc. And those wings are actually quite important. You want to know how does the likelihood look like if you go out into the outer regions. So, so having a high efficiency in itself, always accepting points, not a good idea. There's really downsides to this. So don't get carried away by this parameter, by this efficiency thingy. That's not so relevant. Okay, but this is indeed one of the important parameters to tweak when you run an MCMC. That and also the starting value are really important ones. Okay, we're really running out of time. Sorry. Now, wait, let me quickly check if I wanted to do something here more theoretically. But this is an MCMC algorithm. Oh, no, now we're moving Fisher matrix. Okay, but before we do Fisher matrix, which we might not do today, we'll do this. So in order to actually check whether you have a good result, you should not just run one chain. You should run multiple chains. And why is that a useful idea? Anybody? I think I dropped a mic somewhere there. Yes. Very good.
So it experiments with different starting points.
Yes. So having different starting points is important. That's right. Other reasons? And what are you ultimately interested in? When do you believe that you've mapped the posterior? We mentioned, sorry, say it loud.
Convergence.
Yeah.
Cosmological parameters.
Convergence, yes, that's right. Did you want to say the same thing or something else?
Yeah.
Right. So you want the distribution, the target distribution to be stationary, right? And what better to probe whether something changes if you run 2 things and they agree. So we're doing this very quickly. Let's see. I hope I didn't. Sorry, I should reset this sigma, otherwise bad. Okay. Move, move, move. Oh, still running. Okay, that happens if you set n eters to 10,000. Oh, right. There was one other very good comment, which was if you have chosen sigma very, very small because you want to be efficient, what is the trade space? What can you do in order to make the MCMC still walk to the right spot? What do you need to increase? Yeah, number of steps. So it's going to be expensive. Small sigma, even though you have high efficiency, can mean you have to wait really long, lots and lots of steps. Okay, we got this, low efficiency. I'm going to plot it quickly. Nice distribution. You can see even here the tails are actually sampled. So this is not a bad choice overall. And now we're doing this a couple of times. So we're running multiple chains, although not so long. This is short. Looking at it. and we're plotting it. Okay. And so here we see, this is just 100 steps. This is 5 different chains. What do we see here? I mean, okay, it's pretty clear what is plotted here. What's on the y-axis? What's on the x-axis? Sorry, do you have a microphone? Ah, there, perfect.
The y-axis is the value of the parameter.
Yeah.
And the x-axis is the evolution of the chain, the step.
Yeah, those are the steps, exactly.
So after half steps, you see that everybody is on the same distribution. They already converge.
Yeah, that's the beauty of a 1D thing. Kind of converges rather fast. Yes, that's right. And so you can see the different starting values, right? You can also kind of see that these chains have similar sigmas. They have similar step width. This would be defined as the burn-in phase. You would throw this away roughly here. And yeah, you can see that it doesn't change very much, that it is kind of converged. Okay. Now, because okay, so let's close this notebook. There is actually, so I didn't think of all of this myself. I changed a couple of things, but not very much. If you want to read this up, there's a very nice stats lecture from Duke Stats course where there is some additional background on this, and that is linked here. I'm not going to take credit for them. But that was actually, I had a look at a couple. That one was really good. Okay, now I am going to very briefly, for the sake of time, talk about the daemon tool in cosmology, which is the Fisher information matrix. And so MCMC can take a very long time, especially if you probe high-dimensional parameter spaces. And there is one of the very important questions that every funding agency wants to know. Every time you go somewhere and you present your experiment, the question is, what are the error bars on the interesting physics that your experiment has? Right? People want to compare the power and information content of different experiments. And the answer to how you can get this quickly is the Fisher information matrix. But there's a lot of problems with this tool. And in high-dimensional parameters, because it relies on, well, let's have a look at the equation. So one failure mode is convergence. There's other failure modes of this idea. This is a definition of the Fisher information matrix. So it's a second derivative of the log likelihood with respect to the parameters in question. So it is a matrix, so it's ij. Derivative, oh, this is dying as well. Derivative with respect to first parameter, second parameter. So if you have 26 parameters, your matrix is going to be 26 times 26. Just intuitively, what does this second derivative here actually tell you? If you have a likelihood function that, again, well, looks like this, what does the second derivative here really tell you? This is your best fit fiducial parameter. Loud, I am not, no, you can hear me.
It's the curvature, so it's like the error in the...
Not exactly the curvature. What is it about the curvature? Yeah, it's how fast the curvature changes. Yeah, that was probably what you meant, right?
Yeah, so it tells you about the error in the Gaussian case.
That's right. So if you have this and if you compare it to something that's like this, you can see here, that's where the curvature changes more rapidly, more drastically. This is a more informative experiment on the parameter, on the relevant parameter than this one, okay? This will have a higher Fisher information value than this one. So that is the intuitive explanation of what does Fisher actually mean. It determines the change of curvature of the log likelihood function. Okay, and most of the times, and it also starts out from the assumption that the likelihood is actually Gaussian, multivariate Gaussian. That comes into play. And not just that, it also approximates the posterior as a Gaussian, right? Which does not need to be true. And so you can imagine when people went to funding agencies and said, hey, I have the dark energy survey, would you please give me money for that? And they show the Fisher information matrix of some very high dimensional parameter space, somebody could have said, well, are you sure that the posterior is going to be Gaussian? I mean, even if you buy that the likelihood is Gaussian, is like something like this. Are you sure that this is a good parameterization? And people then argue, well, maybe it's not Gaussian out here where something weird happens, but it is pretty Gaussian at the peak. And that is not a bad approximation. So that kind of motivates why the Fisher matrix is acceptable as a first order quantification of what is the information in your experiment. Some other properties of the Fisher matrix. So the Fisher matrix is the inverse of the parameter covariance matrix. What does that mean, the parameter covariance matrix? We've heard of this covariance matrix over here. That's not the parameter covariance matrix. This is in data space. Right? Data minus, well, actually model more, fine. This is the inverse of the data covariance matrix. So if we have weak lensing 2-point functions, this is a covariance matrix of that. But the Fisher matrix is the inverse of the parameter covariance matrix. So what does that mean? Anybody? Any idea? Ah, you need a microphone, sir.
You can also write the posterior as a multivariate Gaussian. So this, in that expression, that the covariance matrix that enters there is the parameter covariance matrix. So.
Yeah, that's right. Yeah, so you can also write the posterior as a multivariate Gaussian. That's exactly right. How would you do that in practice? Say if you had run a chain. You have a chain, you have 26 parameters, so you have 26 columns, and then you have a gazillion numbers, 1 million steps, 1 million rows. How would you get a covariance matrix from that? Any idea? Yeah, you also need a microphone, but that was a very good answer. So I'll wait and no. Let him have the glory. It's good.
Yeah, you use the estimator of the covariance matrix, then you use the points from your chain to estimate it.
Yeah, it's estimated in a very similar fashion. You take the mean of the parameters and you look at what is the variance, right? You have a whole set of realizations. You get, just let's do it with 2. So you have omega matter, you have sigma 8. It's a very poor sigma. So you get a gazillion values here. Those are all the steps of your MCMC. So this MCMC only has 10 steps. You calculate the mean, you calculate the variance, you just calculate the covariance matrix. Those are your data points. It's very easy. So from a chain, you can just get a parameter covariance matrix, and you can invert that, and that gives you the Fisher matrix. But that has the assumption that these are distributed in parameter space as a multivariate Gaussian, which doesn't need to be the case. If you were to plot them, you would see, and you do see that in the first slide that I showed, it's not really a Gaussian. It's not an ellipse. It's got wiggles. Okay. Then there is a question of some parameters are more interesting than others. So the funding agency is going to ask you, well, okay, you give me these 26 parameters. I don't care about all of them. I just want to know what's the error on W. And there is 2 ways how to get that, marginalized and unmarginalized. Marginalized means you include the uncertainty of all the other dimensions in this value, and unmarginalized means you only take you take the error of W while keeping everything else fixed at this fiducial value. You always calculate the Fisher matrix at a fiducial value. You can fix all of the parameters, and then you want to know the uncertainty of W while keeping everything else fixed. And that's obviously going to be much more narrow, you will have a much smaller error bar compared to if you marginalize over the uncertainty of the others. You can get that information from the Fisher information matrix. If you want to get the marginalized one, you take the square root of the inverse of the diagonal of that parameter. So if you're interested in the dark energy parameter, and that is the 5th parameter in your chain, I is 5. And unmarginalized, you just do 1 over the square root of the of the Fisher matrix. Okay, and this is the last slide, very punctual. This is an example for a Fisher matrix 4-week lensing. They all look a little bit different if you calculate the Fisher matrix for supernovae, if you calculate it for galaxy clusters. This is the one for weak lensing, and you can see that this is a sum over the Fourier modes L. This here is now a CL. This is a power spectrum, and it is the derivative of the power spectrum with respect to these to this parameter, so to pi. So this is just one entry in your overall large matrix, right? Let's say this is I, this is J, it's this value over here. So you take the derivative of the CLs with respect to that parameter, multiplied by the data covariance matrix here. You really have to know your covariance matrices when dealing with Fisher matrices. Multiplied again by the derivative with respect to the other parameter. So you can see that this involves numerical derivatives in a very high dimensional parameter space. And that is one of the main problems of Fisher matrices, right? This is really the main problem. So this is what you have to implement into the code. And numerical derivation, right? And you have 5 steps. You look at what happens, and you calculate the derivative. There's formulas for that. But this is unstable, and it depends crucially on what is the step width that you choose in parameter space. And so what people do when they calculate these Fisher matrices is they change the step width, and they see when does the Fisher matrix become stable. You start with a broad step width, calculate the derivative, you decrease it, you look when it gets stable, but it doesn't really get stable, and at some point it goes haywire again when the step width actually becomes too small. And there's no good recipe for exactly finding out what is the right step width. So that's one of the uncertainties in Fisher matrices that allow this method never to be more accurate than, say, 10%. That's already pretty precise for something like that. Okay. Yeah, if you want the Fisher matrix for a subset, there is it's not quite as easy as just taking that subset of the Fisher matrix. You actually have to invert it. So you get the parameter covariance matrix, then you take the subset, then you invert that subset. That gives you the Fisher matrix of that subset of parameters. That's something that has gone wrong in the literature, for sure. People are sometimes not really aware how to properly take these subsets when quoting error bars. Okay, but in principle, I would like you to keep in mind that this is a useful tool, and it is exactly what happens when you type run Fisher in the desk SRD package. And we'll get to that, unfortunately, then tomorrow, because today is already over. Thank you.
To do that before we actually launch the survey, because we're trying to estimate exactly the uncertainty. But in order to run the chain, I need some data from the survey.
Yeah.
So how do I solve that?
No, that's right. So I just mentioned this. This is not a procedure you would implement in reality. This is just to make clear what the connection is. Yeah, it's really just that. I mean, having said that, at some point in this science requirement document, I actually needed to, I needed a chain in order to use the plotting routine that I wanted to use. So I took the parameter covariance matrix and just created a chain from that. And then you can, then I was able to plot it nicely because this plotting routine was only able to handle chains and not Fisher matrices. Also, if you want to have a cheap way how to include Planck priors into your likelihood analysis, right? You can just download the Planck chain, and you compute the parameter covariance matrix of that, and you can feed that into your likelihood code it's super fast, right? And having said that, I should mention there's a very nice paper out there from like a month ago from Tom McClintock, who has done something more sophisticated. Namely, he's taken the Planck chain or any other chain, and he's built an emulator that predicts the likelihood as a function of parameters. So he just samples that chain. He builds, through Gaussian processes, a predictive tool. And that allows him also to immediately give the result of the posterior for Planck without having to do the whole Planck likelihood calculation. Right? So it's very, very nice. in order to include external information. The cheap version would be a parameter covariance matrix. The most sophisticated version is this emulator idea. You just have to make sure that it is sufficiently precise. Yeah. Yeah, you're right. One would not go this way. That's right. Yeah.
Now I'm a little bit confused. Should I, in order to compute the Fisher matrix, use the inverse parameter covariance matrix? I mean, taking all the points that change and then compute the inverse of the covariance matrix, or should I use the data? So I'm a little bit.
You would use this, right? So if you would not, this is kind of a similar question. You would not first create the chain and then get the parameter covariance matrix and then get the Fisher matrix. That's not what you would do. Because in order to get this, you have to build this huge complex machinery. And that's, I mean, at that point, you can just do the chain, right? There's no need anymore for Fisher. Fisher is a fast way. So, and if you want to do a weak lensing Fisher matrix, then you can calculate that this is the relevant formula, and this is what you would implement into the code. So what do you need? It's exactly in the desk SRD. You need a covariance matrix. That is in this zip block, in this zip file that I mentioned. And you need a code that calculates the derivative of the power spectrum with respect to the parameters. So you have to implement this kind of a 5-point derivative, numerical derivative function. And then you can just sum up over L, and you get the Fisher matrix. And that is much faster than running an MCMC, but it has the problems that I mentioned. Does that help? Okay.
Also, what I could understand that it's this Fisher matrix is good in the presence of the assumption of the likelihood. How can I assess the error without using this assumption of the Gaussian of the likelihood?
So you cannot. I mean, it assumes that the likelihood is Gaussian. It assumes that the posterior is Gaussian.
Yeah, but beside this kind of the Fisher matrix, I mean, using another technique.
Okay. There is no short technique. Not really, no. Well, not that I'm aware of, I should say. Yeah, not that I'm aware of. The thing that that's one of the reasons why we're building these simulated likelihood analyses, because we don't want to do Fisher anymore. We want to get a chain realistically as if you had a true data vector. And that should be more precise. It is definitely more precise in high-dimensional parameter spaces where things are just no longer Gaussian. And perhaps one other fast method would be to combine the emulation idea with running a chain. So you would pre-compute the posterior at a couple of points, smartly selected points in this high-dimensional space. And then you would, through Gaussian processes, develop a fast predicting tool. And for forecasts, that might be fine. So then you don't have to run a million steps. Then you just do the calculation on like 1,000 points in parameter space, right? That doesn't take a lot of time. And then you run a chain where you get a return within milliseconds, microseconds. So that's actually a smart way to go for the future. And people are working on that, yeah.
In the previous example of the Markov chain, if I relax my prior, what should I expect from my efficiency?
If you relax your prior, what should
Because I saw that the efficiency is a bit higher if I relax my prior, but I don't understand why it happened.
You saw what behavior?
The efficiency is higher. It increases.
I think it's related to whether I don't think it's to first order related to the prior directly. I think it might be related to what the discrepancy is between the prior and the likelihood. And if you relax because ours were a little bit discrepant, if you relax the prior, then you might get a higher acceptance rate. I could see that. Yeah. Sorry, did you have a comment or?
think sigma, because I tried the same thing.
You
So
tried the
when
same?
sigma was small, when you said burnout, what was the phenomenon when it was very?
Yeah, but you were talking about the prior width, and you were talking about the sigma width of this proposal, of this.
Yeah, but I tried with a flat prior, and I
okay.
saw very high efficiency.
Okay. Yeah. So I think the prior can decrease the efficiency if they are kind of separate. If there is a tension between the data and between the likelihood and the prior, I think then this can happen. Yeah.
So when you say that to use the Fisher matrix, we need a Gaussian distribution, it's not in its general form, right? If we get the Fisher matrix, like the general form of the Fisher matrix, it could apply to any distribution. But in this
the Fisher matrix assumes a Gaussian distribution. It's not, you don't need it anywhere. You just, the whole calculation, the whole methodology of Fisher assumes a Gaussian likelihood. Okay. Sorry. Did you have a specific example in mind where you thought it was not the case, or
I'm gonna think about it, and I'll talk to you later.
Okay. Yeah. Sounds good. Yes. That sounds good. Yeah.
You're going to talk about ellipses later.
About ellipses?
Yeah.
No, not yet.
From Fisher? No.
I can talk about ellipses.
Because ellipses are all ellipses. They're not banana shapes or anything.
So I mean, that's the posterior, right? So in the posterior, that if you were to, so a Fisher matrix, right? You can plot an ellipse. You cannot plot a banana. That's just not, you can't do that with a matrix. And that automatically implies that the posterior that you get from a Fisher matrix will always be Gaussian. But in addition, the derivation of this requires assumes the likelihood to be Gaussian. And that's something I'm happy to talk about later as well. Yeah.
Okay, thank you.
Okay, about the burning. If you don't consider the burning, how is your results affected?
If I don't consider what?
If you don't burn out some of the information, how is your result affected, the final result?
You mean, so are you talking about this spinning here that I have automatically, or?
No, I'm talking about the burning. When you run the chain, different chains, you realize that they started from a different starting point. And at a point, you said that we can burn in some of the information, we can remove some of the information. Yes. And I'm asking how would that affect your results? And also, how will you know how much of this information should I burn out?
Yeah, so the burn-in phase is a little bit is hard to define exactly where to cut it, right? But you would assume that that this does not really affect your plots afterwards anymore. So if you remove that, I mean, if you are in a you might see in a 2D projection at some point something that walks over here, right? And then after, if you cut out the first 100,000 points, it only stays here. So there's a couple of diagnostic tools where you just plot the posterior as a function of removing steps. And again, if this is stationary, if this doesn't change anymore, you're happy with it. Right? But if you see that it is still changing later on, then you have not even gotten out of the burn-in phase. Then you are still in the burn-in phase, and then your chain needs to be much, much, much longer. So it is a bit of empirical processes, how you figure that out in practice. Yeah, sorry.
Because from what the result you showed, about 20% of it should be just ignored from the graph you showed initially. Because most of I've seen a lot of chains, after that, all that they do is to burn out like 30% of it. They don't plot any graph, they don't show any different chains, but all that they do is to just ignore about 30% of the information. And I'm a little bit worried about that. That's why
You're worried about throwing out 30% of the steps?
Yeah.
Why? I mean, the plotting, because the information is not necessarily, I mean, this is not real information, right? This is still where the MCMC is trying to find the maximum likelihood point, and then from there on it starts to branch out and to map that precisely. So for plotting, for example, you don't need very many steps. Usually for an MCMC we have like, I don't know, I'm now running things for 3 million steps, and I throw out 500,000 at the beginning, but it doesn't change anything, right? I could throw out 1 million and it doesn't change anything, because for plotting itself, almost 50,000 points are fine. It's like you get nice plots, actually. So, I mean, you are right that if you have too few points, right, and or if you thin the chain too much, there are sometimes where people take out every 5th point or something, or every 2nd point. There is some problems associated with that, but usually you're fine if you do these convergence tests. Yeah.
I was wondering, how much should we rely on the assumption of a Gaussian likelihood? Because we just saw that the likelihood and the prior can alter too much the posterior. So are we assuming a Gaussian likelihood on the data just because of the central limit theory?
Yes. Yes. I mean, there's the question whether how much should we be worried is the right one to ask, and it is being researched right now. And yes, it is the central limit theorem that is most times invoked for this. I mean, you know, if you look at how many functional forms are out there, it's not that many. And if you and it's very hard to come up with non-parametric forms of the likelihood. That's actually these ideas exist, but they are very hard. So you can look into approximate Bayesian computation if you are interested in that. But that has some horrible other properties, like it doesn't converge very fast, etc. But in approximate Bayesian computation, you avoid making any kind of assumptions on the functional form of the likelihood. You make some other assumptions that are equally bad, but that one you avoid. My personal take would be if the difference, or if the difference between the true likelihood and the one that we assume doesn't matter so much, we should just go with it. But whether it matters or not is researched right now. Yeah.
Thanks.
More questions for Tim? So if not, let's thank Tim again and go for coffee.
Thank you.
Okay.
Let's return this.
I need it tomorrow again. It's like
Get it tomorrow.